And actually at this point, we're going to kind of transition the course into dealing with sort of the broader ecosystem of RL-related problems. So we sort of finished the discussion of core reinforcement learning algorithms, core algorithms for model-free RL and for model-based RL. Today I'm going to discuss a particular connection between optimal control, reinforcement learning, and probabilistic inference. Next week, I'm going to tie this into inverse reinforcement learning, which is the problem of analyzing behavior and determining what objective that behavior is trying to optimize. And then we'll have some discussion about things like transfer, exploration, meta-learning, and so forth. And then in the last couple of weeks of the course, we'll actually have guest lectures from researchers that are doing cutting-edge research in this field. So at this point, these topics will really be more focused around current cutting-edge research things that are partly meant to kind of give you some ideas for things you might want to try out in your final projects and things like that. In terms of the homeworks, we'll have homework 4, which will cover model-based RL, and we'll have one more homework after that, which will probably cover exploration, and that's something that will be discussed a couple of lectures from now. Okay, so some class notes. The important thing is that homework 3 is due soon, October 21st, and as I mentioned before, make sure you start on this one early. It takes a little while to get, especially the image-based Q-learning stuff, to get it to finish running for 3 million steps. All right, so today's lecture. Today, we're going to talk about this question. Does reinforcement learning and optimal control provide a reasonable model of human behavior? So far, we've mostly talked about the problem, given some objective, figure out how to get an agent to satisfy that objective. Now we're going to actually begin discussing the inverse problem. Given some behavior, figure out what objective that behavior is actually trying to optimize. And we'll see next week why this might be useful in many cases. And one of the things that I'm going to talk about is how pure optimal control or pure reinforcement learning, as we've discussed it so far, often doesn't actually provide a good explanation for the behavior that we observe in the real world from biological intelligent agents like humans and animals. And I'm going to discuss how we can derive optimal control and reinforcement learning as well as planning from more of a probabilistic perspective. So oftentimes when we observe some process in nature, that process is maybe governed by some underlying mechanisms, but then the process is also stochastic. And maybe we have noisy observations of the process, and the process itself has noisy dynamics, so it really helps to model as a probabilistic model. This is going to lead to a new formulation of reinforcement learning algorithms that looks a lot like the ones we've seen before, but in a subtle way is a little bit different. And we'll see how this can give rise to new kinds of reinforcement learning algorithms and also new kinds of algorithms for analyzing behavior for inverse reinforcement learning. And then next week we'll really talk about core inverse reinforcement learning algorithms based on these ideas. So today's lecture is going to be a little bit more conceptual, a little bit more theoretical, and then we'll have more concrete algorithms next week. All right, so the goals for today will be to understand the connection between probabilistic inference and optimal control, and understand how specific RL algorithms can be instantiated in this framework and how they differ from the classic RL algorithms that we've discussed before. And then maybe understand a little bit about why this might be a good idea or why we should care about this sort of analysis. Okay, so let's start with a little bit of a discussion of optimal control as a model of human behavior. So for actually quite some time, people who study human behavior, human motor control, psychology, that sort of thing, have given a lot of thought to the question of whether human behavior, or animal behavior for that matter, can be explained as some sort of optimization process. So this is, for example, some very classical photographs by Edward Muybridge studying, in this case, human biomechanics. So this is a high-speed recording of a person running. And this kind of thing, you can kind of look at it and try to figure out, well, presumably the gait that the person is executing is optimizing for some particular objective. Perhaps it trades off metabolic energy against their desire to maintain some particular set point speed, etc. And more recently, in the 21st century, people have actually continued the study of this question with more modern computational tools, analyzing the degree to which, for example, the particular strategies people use to reach desired locations for walking reflect maybe some principles of optimality. In fact, the principle of optimality has been one of the most powerful concepts in recent years to explain human and animal motor control, both for locomotion tasks and also for manual manipulation tasks. For example, human reaching motions can be modeled fairly accurately with a probabilistic variant of optimal control, which is actually what we'll discuss today, as well as kind of higher level behaviors. So for example, probabilistic approximately optimal models have been used to describe how, let's say, taxi drivers choose to navigate street networks in Pittsburgh. All right, so what's kind of the idea behind all this stuff? Well, the idea is basically this, that we've learned that if you have a reward function and you have either a model of the world or the ability to interact with a simulator of the world, you can extract an optimal or near optimal plan by solving an optimization problem. So in the model-based kind of optimal control framework that we discussed a few weeks ago, this is the kind of problem you might be solving. In the more classic reinforcement learning formulation, this is the kind of problem you might be solving. But in both cases, it's basically given some reward function, solve an optimization, get back a plan or a policy. So that's what we've been doing so far. But if you want to use the principle of optimality to explain behavior that you're observing, what you're really doing is you're saying, well, if you assume that the person is doing this, can we figure out this? Can we figure out the R that caused them to do what they actually did under the assumption that they were optimizing some objective? So you could imagine doing this. I mean, the actual kind of optimization framework needed to infer R given a pattern of behavior is a little bit complex, and that's what we'll describe next week. But let's for now just assume that you can do this. So you basically say, you know, I have a monkey in the lab. The monkey is doing some kind of motor control task. Maybe it's using this little joystick to steer the little green dot to line up with the red dot. And you know, here's where it starts. Here's the goal, and you expect the monkey to basically do this. And then you say, well, let's set up my optimization problem from the previous slide. Say the monkey is doing trajectory optimization. Figure out the R that causes the monkey to reach the target, and that's sort of your explanation of what the monkey's objective is. So that's all fine and good, and in general the principle of optimality does provide a pretty powerful explanation for actual behavior observed with humans and animals. The problem is that if you actually try to do an experiment like this, the monkey is not going to perform this nice straight black line. The monkey will do something like this, or maybe a little bit like this. So then the researcher studying this monkey will look at it and say, well, something is wrong here. I expected this monkey to be optimal, and it seems to be doing some other random stuff that I didn't expect. So the trouble with this is that the monkey is doing the task, but like most animals and people, it's not actually optimal. It's a kind of approximately optimal monkey. And that's because the monkey has some things that it cares about a great deal, like it cares about reaching the target and getting a little bit of juice as a reward. And there are other things that the monkey is a lot less concerned about, like, you know, it's probably a pretty lazy monkey, and doing this perfect straight line path every time takes a lot of mental exertion, and it would rather just kind of do the minimum effort necessary to get the juice rather than really overexert itself. So the crux of the issue here is that some mistakes matter a lot more than others. And you know, actual, real biological motor control is complicated. And there are a lot of complex stochastic processes going on. And it takes quite a bit of cognitive effort for the monkey to really suppress all of that and perfectly execute this beautiful straight line path. A lot easier for it to just kind of do a good enough job by doing this kind of wiggly thing. So some mistakes matter a lot more than others. The monkey doesn't really care about giving you this straight line path. It cares about getting the juice. So its behavior is going to be stochastic. On a good day, it'll do one thing. On a bad day, it'll do another thing. On trial 1, it will do one thing. On trial 2, it'll do a different thing. But it's much more likely to do good stuff than bad stuff. So it knows it wants the juice, and it's going to reach that target with pretty high probability, even if it takes a kind of a wiggly roundabout path to get there. So now we might ask, well, can we actually write down a new notion of optimal control, a stochastic notion of optimal control, that will result in solutions that produce these wiggly blue lines, but assign very low probability to a path that doesn't actually reach the target? And this is not something that's actually covered by any of the formulations we've discussed so far. So if you set up policy gradient, you can accommodate stochastic dynamics, you can train a stochastic policy, but at convergence, that policy will prefer to do the straight line path. So what we really need in order to model the possibility that the monkey, or in general the agent that you observed, might randomly choose to do other things, but is much more likely to do things that actually reach the goal, what we need to do is we need to set up kind of a probabilistic model, a probabilistic graphical model for decision making that allows us to explain why good behaviors are more likely than bad ones, but a variety of different good behaviors might all be equally likely. So before, the model of decision making that we had was essentially this thing, or a stochastic version thereof. The stochastic in the sense that the rewards are being maximized in expectation under stochastic dynamics. But that's no good, because that has just one solution, which is the black line, which is not what our monkey is actually going to do. So we don't want that. We want something that can explain why the monkey might choose to do slightly random, slightly different things. So we need a graphical model. We'll begin with a graphical model that we already understand, which is the graphical model that describes the relationship between the states and actions. These are the things that the monkey really has to reason over. So there are, at every time step, there's a state and an action. They influence the state at the next time step according to the dynamics P of S prime given S comma A. So that, we've already seen that. We already know that that needs to be part of our model because that's how the world works. So we could write down the following probability. We could say, well, what's the probability of seeing a sequence of states and a sequence of actions, which we can abbreviate as tau. So what's the probability of seeing a trajectory tau? That's not quite enough by itself, though, because the monkey isn't just doing random things. It has an intention. It's trying to reach that red dot so that it can get the juice. So there's some more variables in the system than just states and actions. There's something that represents what the monkey actually wants to accomplish. So we need to add some variables to model this. There's no assumption of optimal behavior if we just ask this graphical model, what's the probability of a sequence of states and actions? So for this graphical model, it'll just tell us, is this sequence of states and actions physically possible? Which doesn't account for intent. So if we want to account for intent, let's add something. Let's add this variable that I'm going to call script O. And I'm going to call it O for optimality. And I'm going to add one of these variables at every single time step. And what these variables represent is whether or not you're being optimal. It's a binary variable. It's either true or false. If it's true, that means you're trying to be optimal. If it's false, that means you're just doing random stuff. So we might believe that the monkey, if it's a good monkey, it's trying to be optimal, but it's within the scope of all the things that it considers to be optimal, there's quite a bit of variability, which is why it might be a little bit random. You can also think of this as intentionality. You can think of this variable as denoting whether you're intentionally trying to do something versus just doing random stuff. And we're going to put one of these things at every time step. We don't have to do that. We could have just put one global variable that says O for everything. But it turns out that having this thing at every time step will make it very convenient for us to factorize our notion of intentionality over time and yield a particular formulation that resembles the reinforcement learning problems we've seen so far. The high-level intuition is that reward functions factorize over time, and we know how to handle reward functions, so we want to get something that factorizes over time. But it's a choice. It's a design choice so far. Okay, so what we're going to want to do is infer the probability of seeing a trajectory given that our monkey is optimal at every single time step. So this probability, this is our generative model of the monkey's behavior. So if we set up a good model, we would expect P of tau given O 1 through capital T to assign high probability to the monkey's seemingly stochastic behavior. Now we have to choose a form for this node. We have to choose a form for P of OT given STAT. And we're going to make what will at first seem like a slightly weird choice, but later on we'll see that this slightly weird choice gives rise to a very elegant mathematical formulation. So remember that OT is a binary variable, and we're going to say that the probability of that variable being true is equal to the exponential of the reward at state ST and AT. You need a mild regularity assumption for this to be reasonable, which is that the reward is always negative. But if your reward is sometimes positive, just subtract the max and make it always negative. That's totally fine. So now you'll just say that the probability of OT being true given ST and AT is equal to the exponential of the reward at that time step. Kind of a weird choice, but let's go with it and let's see what it gives us in terms of the equation for the posterior. So remember, we want P of tau given O1 through T. And from the definition of conditional probability, we can write that as the probability of the joint divided by the probability of optimality at all time steps. So up to a normalization constant, I can write that out as the probability of the trajectory a priori. So that first term, that P of tau, this is basically how likely is the trajectory to happen according to the laws of physics. So that means that trajectories that are physically impossible get a probability of 0. Trajectories that are physically possible get some non-zero probability. If you have deterministic dynamics, this first term is really just an indicator for whether this is feasible or not feasible. And then the rest of this joint distribution is just the product of the probabilities of OT given SDAT. And the convenient thing about products of exponentials is that they are equal to the exponentials of the sums of the exponents, which means that we can turn this product of exponential r into an exponential of a sum of r. And now we get something that begins to have a little bit of a reasonable, intuitive explanation. So if we pretend for a minute that our dynamics are deterministic, this first term P of tau just turns into an indicator for whether or not our trajectory is physically possible. And the second term is the exponential of the total reward along that trajectory. So that says that the probability of the monkey producing a particular motion is 0 for everything that's physically impossible, because you don't have a magical wizard monkey, you have a normal monkey. And then for everything that is physically possible, the probability goes with the exponential of the total reward, which means that the most rewarding, the optimal trajectory, is the most likely, and then other trajectories become exponentially less likely as they become less rewarding. So if there are millions of different trajectories that all result in the monkey getting its juice, that's the thing it really cares about, and it will assign about equal probability to all of them. Now maybe the monkey is a little bit lazy, so it will prefer somewhat shorter paths over longer ones, but the difference between those is not nearly as large, so even the slightly longer paths still have a non-trivial probability. And now we have something that resembles a plausible probabilistic explanation for our suboptimal monkey. Does anybody have any questions about this probabilistic model? Do you guys believe that this is how monkeys actually behave? Okay, a lot of skeptics in the room. Okay, well, we can come back to the monkeys later. But since this is a computer science course, what I really want to do is tell you about some algorithms that we can use to deal with these kinds of models. All right, so for basically the first half of this lecture until the break, what we're going to do is we're going to deal with this probabilistic graphical model and try to understand how we can actually do inference in this model and what the resulting inference algorithms actually look like. As a preview, they'll have an uncanny resemblance to some algorithms that you've seen before. But before I do that, let me talk a little bit about why this is interesting, other than allowing me to tell you lots of cute stories about monkeys. It's interesting because it can model suboptimal behavior, which is very important for inverse reinforcement learning. So if you observe somebody doing something, people do random stuff. And that random stuff isn't always very tightly informed by our objective. So, I might be going to the grocery store to buy some groceries, but my mind wanders a little bit. Maybe I get distracted. Maybe I, stare off at the clouds for a little bit. But that doesn't mean that my objective has changed. I'm just kind of being a little bit random, and people do that. So if you can't represent the fact that your agents might exhibit suboptimal behavior, it's very difficult to infer their objectives, which is what we have to do in inverse RL. And inverse RL turns out to be crucial for more sophisticated forms of imitation learning. So inverse RL is a very important basic algorithmic framework, and you really can't do that unless you have some notion of why the agents you're observing might behave not perfectly optimally. This kind of framework also allows us to apply inference algorithms to solve control and planning problems. So probabilistic inference is a very, very well-studied field. There are a lot of exact and approximate methods in probabilistic inference, and connecting this to reinforcement learning and planning gives us a lot of additional theoretical and algorithmic tools to bring to bear. And it also provides us with a little bit of an explanation for why we might prefer stochastic behavior over deterministic behavior, which could be quite important for some topics in exploration and in transfer learning. So if you have a single specific problem you want to solve, you know everything about that problem, you know all the dynamics, you can generate infinite samples, then a deterministic policy will be optimal. But in more practical problems where things like exploration are a challenge, so you might want to be a little more stochastic than usual, or in transfer learning, where you might want to use what you've learned to apply it to other problems, then actually being a little more random can be very helpful, and this can give us a tool for that. Yes?
So if you have a long time period, then the agent may not have the foresight to plan for long time periods. In that case, he will always be suboptimal.
Right, so the question was, well, maybe another source of suboptimality is that if you have a really long time horizon, you essentially have to reason at different levels of detail, and since you can't perfectly plan out all the details of your behavior for a really long time horizon, that might be a source of suboptimality. That's absolutely true. And this kind of model does not account for that. So this is not a bounded rationality model. This is actually a kind of stochastic behavior model. Okay. So let's talk about how we can perform inference in this kind of graphical model and recover an equation that describes the most likely behavior given that these optimality variables are set to true. So this graphical model really has two types of conditional probability distributions. It has the probability of ST+1 given STAT, which is your dynamics, and it has the probability of OT given STAT, which is as I've said before, the exponential of your reward. There's also this one little detail, which is at the very first time step, you have a P of S1. But that's not really all that important because it only happens once, and the rest of these happen every time. But there is one more CPD, which is P of S1. All right, so how do we do inference in this thing? So there are three kinds of inference questions that we're going to want to ask. The first question that we're going to ask is, how do you compute a backward message? It might at first seem a little strange that this is the first question to ask, but it's the first question to ask because it really helps us answer all the others. So a backward message, I'm going to denote as beta t, as a function of STAT, is the probability of the optimality variables being true from the current time step t until the end, given your current state in action. So while this might seem like a slightly arbitrary question to ask, we'll see afterwards that it's a very, very useful quantity to calculate. Because if you can calculate the backward message, you can actually recover the near optimal policy in this graphical model. And that's the second question. The second question is, how do you compute a policy, P of AT given ST, comma, O1 through capital T? So this conditional distribution is the equivalent to the optimal policy under this graphical model. It's answering the question, given that you're at this state and given that you are being optimal always, what is the probability of taking a particular action? And answering this question is essentially the equivalent to optimal control or reinforcement learning in this stochastic framework. And what we'll see is that calculating these backward messages helps us answer the question number 2. So if you can calculate the backward messages, it turns out to be very easy to figure out the near optimal policy, P of AT given ST, comma, O1 through capital T. Now there's another question you could ask, which is P of AT given ST, not conditional on anything else. That's not a very useful question, however, because that's just asking which actions can you take. And the answer to which actions can you take is all of them. Right, so if the monkey isn't trying to do anything in particular, it can just flail its arms around randomly. What we really care about is which actions is it likely to take if it's trying to get the juice. The third question that we'll study is how you compute a forward message. Now this one is a little bit peculiar. The forward message tells you what is your probability of landing in a particular state given that you've been optimal at all of the preceding time steps. You don't need the forward message to figure out the policy. However, the forward message turns out to be very, very useful for figuring out which states the optimal policy lands in. And while we will not need the forward messages in order to solve the forward reinforcement learning problem, we will need the forward messages to solve the inverse reinforcement learning problem. So today I will describe how we can calculate the forward messages, and then on Monday I'll describe why you might actually want to use them. Okay. So let's start with the backward messages because these are by far the most useful. So the backward message is defined as the probability of the optimality variables from the current time step until the end, given the state ST and AT. And in general, when faced with these kinds of queries, what do we do? Well, we have a bunch of hidden variables, which are all the other states, and we need to put in those hidden variables, integrate them out, and re-express the message that we want in terms of the quantities that we have, which are these CPDs. So the game that we're going to be playing is we're going to try to express beta in terms of the probability of a transition and the probability of optimality, this exponentiated reward. And since this is going to be a recursive procedure, in terms of the beta at the next time step. So we'd like to turn this into things that we know. So the first thing we're going to do is we're going to put in the next state. So for any distribution, I can always put in another variable and then integrate it out. So I'll put in st+1 and I'll integrate it out. And now what I'm going to do is I'm going to break these things apart using the chain rule of probability. So via the chain rule of probability, I can take the all the future optimality variables, so from t+1 to capital T, and I can condition them on just st+1. I know I can do that because from the structure of this graphical model, if you remember d-separation, OT is conditionally independent of OT+1 given st+1. So I can do that, and I can remove all the other stuff on the right of the conditioning bar. Then I have P of st+1, and P of st+1 is conditioned on st80, so that's this bit. And then I have the remaining optimality variable at time step t. So all I've really done here is I've applied the chain rule of probability to break this up into three parts. The probability of all the future optimality variables given the next state, the probability of the next state given the current state in action, and the probability of the current optimality variable given the current state in action. So this thing I know, this is just my exponentiated reward, so I can stop worrying about that thing. This bit I also know for now, that's my transition dynamics, although we'll see how we can derive model-free algorithms on this basis also. So all I'm left with is this first weird term. And this first weird term, the P of OT+1 through capital T, that one I can insert into it the action, so I can put in P of OT+1 to T given st+1 and AT+1, and then AT+1 given st+1. So the first term in this product is just beta at the next time step. So this is beta st+1, AT+1. So if I'm proceeding recursively from the end to the beginning, I would know what this is by now. So I'm just left with that second term, the probability of the action given the state. But remember what I said before. The probability of the action given the state, not conditional on anything else, is just describing what can you do. And the answer to what can you do is whatever you want, right? So we can actually, for now, assume that this term is just a uniform distribution, meaning that it's a constant. We'll see later on why assuming this is uniform doesn't actually reduce the generality of this formulation. But for now, just take my word for it. Let's just take P of AT+1 given st+1 to be the uniform distribution, which means it's a constant, which means that we can essentially disregard it for the purpose of inference. So now we've expressed beta st_at in terms of beta st+1, at+1, and the dynamics and the exponentiated reward, all things that we know. So if we start at the very last time step, of course, beta st_at is just equal to exponentiated reward because there's only one time step to go. And at the second to last time step, we use this derivation to express it in terms of the last time step beta, the dynamics, and the exponentiated reward. And then we can do this recursively all the way to the beginning. Any questions about this derivation? Yes?
So in the derivation, it assumes that we know those probabilities exactly?
Right. So exactly. So for now, we're not doing anything with learning. We're not doing anything with model-free. We're just assuming all probabilities are available to us. Okay. Later on, we'll see how these integrals can be approximated without knowing the true dynamics. And the spoiler is that you do it with sampling, the same way you do everything. OK, so here's the algorithm. From time step capital T minus 1 to 1, express your beta T st_at as your probability of optimality. So that's this thing times the expectation with respect to the next time step. So that's accounting for this thing of what I'm going to call beta T+1 st+1, which is this term right here. And then calculate your state-dependent message by taking its expectation under your action distribution. So that's this thing right here. So calculate the state action message, calculate the state message, go one step backwards, and then calculate the state action message for the previous time step using the state message from the next time step. And then just keep going and going and going until you hit time step 1, and then you're done. Then you've got all the backward messages. Now, at this point, some of you might be thinking this might start to look a little bit familiar. Let's take a closer look at the backward pass. So this is what I had on the previous slide. And I'm going to introduce some terminology with some very loaded letters. I'm going to say the log of beta t st, I'm going to call that vt of st. It's a good letter. I'll use the letter v. And I'll use the letter q to denote the log of beta st at. So these are some arbitrary choices. These are kind of my two favorite letters in the alphabet, so I'll use them. And then I'm going to express these equations in log space. So let's start with this one. Let's start with the equation that calculates the state message in terms of the state action message. Here I've taken the log of the right-hand side, and I've written it out like this. So if I were to take the log of the left side and the right side, it turns into the log of the integral of the exponential of log bt, stat. Because remember that p of at given st is uniform, so that's just a constant in front of this thing. All right, now you might be saying that doesn't look particularly interesting. I mean, that's the log of the integral of an exponential. But logs of integrals of exponentials actually have some interesting properties. Imagine that the quantity inside this exponential becomes very large. So let's say I have some numbers for q of stat, and I multiply those numbers by 1,000,000. When you exponentiate those numbers and you add them together, the biggest number is going to dominate. And in fact, the bigger those numbers are, the more the biggest number dominates. When you then take the log, you're essentially taking the log of the biggest number plus a bunch of other stuff that's really, really small. So as the q's get bigger and bigger, the log of the sum of the exponentials approaches the max, because the biggest value dominates that sum of exponentials, so that when you take the log, the little numbers have minimal impact. So as q of stat gets bigger and bigger, the v becomes more and more similar to the max. We'll have to remember this, because this will be important later on when we have to come back and think about why our monkey was doing that random stuff. But for now, we'll sort of observe this as an interesting factoid, that this log sum exp kind of has as its limiting case the max. Let's look at the other equation. When we express that equation in log space, again, you get something that sort of looks sensible but a little weird. So you get, multiplication turns into addition in log space. So you have the reward that's coming from the p of ot given stat term. And then you have the log of the expectation of the exponential of the next step value function. Well, if you remember the value iteration algorithm, the value iteration algorithm, of course, looked a little bit different. In value iteration, your q function was the reward plus the expectation of the next value, so all those logs and exponentials weren't there. And your value function was the max of your q. Now, we kind of see that this thing kind of becomes a little bit like the max if the q values are big enough. But what the heck is up with these logs and exponentials? Well, one thing we could observe is that if your dynamics are deterministic, meaning that only one next state has a non-zero probability, then this expectation is not actually a sum, it's just the value function evaluated at one state, which is the one state that can happen given your state in action. So then the log and the exponential cancel out. So under deterministic dynamics, q is equal to r plus next v. So under deterministic dynamics, you get exactly line 1 in the regular value iteration algorithm. But under stochastic dynamics, you get this weird thing. So what's up with that? Well, this weird thing is actually a little bit of a problem. This weird thing will describe some behavior that is not quite the behavior we typically want to see in optimal control. The reason is that just like over here, the log of the sum of exponentials looks a little bit like a max. So instead of saying that my q function is going to have added to it the expected next value, it's going to look a little bit like the maximum next value. So this is a kind of optimism bias. This is saying, since you assume that you are being optimal everywhere, what your inference procedure will actually do is just tell you that given stochastic outcomes, the more desirable outcome is actually more likely. So if I believe that I did the right thing and I got $1 million, my probability of having bought a lottery ticket is higher because my probability of having won the lottery is higher. That's just the consequence of posing an inference question like this. And we'll actually see in the second half of today's lecture how this optimism bias can be removed in the stochastic case by employing the tools of variational inference. But for now, we'll just say that in the deterministic case, everything is all good, deterministic dynamics, that is. Later on, we'll deal with stochastic dynamics. All right, any questions about this? OK. So the summary of the backward pass is that you have these backward messages, beta, that are functions of states and actions. They tell you the probability of optimality from now until the end, given your state and action. And you can compute them recursively from the end to the beginning via the procedure that I had before. And the log of these backward messages is sort of Q function-like. It looks a bit like a Q function, and if you squint a little bit and pretend that all your Q values are big and your dynamics are deterministic, you get something that looks a lot like value iteration. Which is not too surprising because this inference procedure is a dynamic programming method for doing inference, so it makes sense that a dynamic programming method for doing inference should look a lot like a dynamic programming algorithm for doing reinforcement learning. They're both just doing dynamic programming. All right. Let's very briefly revisit this question of the action prior. So I sort of swept this under the rug before. I said that P of A given S is just a constant. And you might challenge me and say, well, what if I don't want it to be a constant? So here is the deal there. If the action prior is not uniform, the way that changes your equation is now your V has a Q plus log P of A given S in there. That's the only change that happens. If you have that change, then before your Q function was this R plus log expectation exponential of next V, we can also define a Q tilde, which is R plus the log action prior plus the expectation of the next V. And now I can rewrite my V as the softmax of Q tilde, right? So this and this are exactly the same. And what that means is that if I have a non-uniform action prior, all I have to do is add it to my reward, redefine my reward to be R plus log P of A given S, and then switch back to a uniform action prior, and I get exactly the same equations. So if you're going to choose your reward function anyway, and it's any function of A and S, might as well just fold your action prior into that and not worry about it. This will save us a little bit of space because we won't have to constantly write out this obnoxious term. But if you do have a non-uniform action prior, just put it in your reward, and all is good. All right, let's go to question 2, and that's sort of the real question. How do we actually calculate a near optimal policy from this graphical model? How do we figure out what is the probability of an action given the current state and the fact that we are trying to be optimal throughout the whole trajectory? So this is essentially the policy. This is essentially the pi in this kind of graphical model. So let's work through that. So first we can disregard all the optimality variables in the past because we know that condition on ST, the action is conditionally independent of O t minus 1 through 1. So we can turn that into P of AT given ST O little t through capital T. And then we'll use the definition of conditional probability to write it as a ratio of two terms. The probability of AT comma ST given optimality divided by the probability of ST given optimality. And then what we'll do is we'll apply Bayes' rule to both the top and bottom. I realize that this just turned into an alphabet soup with lots of numbers, but believe me, this is just Bayes' rule. I just applied Bayes' rule to the top, and I applied Bayes' rule to the bottom. So we all know Bayes' rule. And when I apply it to both the top and bottom, I have these denominators, P of O little t through capital T, and they appear on both the top and bottom, so they just cancel. So then I'm just left with the product of two ratios. So here are the two ratios. Probability of optimality from now until the end, given the state in action, divided by the probability of optimality given only the state, times the probability of the action and the state divided by the probability of the state. The second ratio, by definition of conditional probability, is just P of AT given ST. And we know that P of AT given ST is our action prior, which we've said is just uniform. So that second ratio doesn't matter. And the first ratio is quite nice because the definition of our backward messages was exactly those terms. So beta STAT is the numerator, beta ST is the denominator. So that means that I can write this as the ratio of the state action backward message and the state backward message. And that's why we needed those backward messages, because once we have them, we can express the near optimal policy simply as their ratio. That is quite convenient. So pi of AT given ST is just the ratio of our backward messages. Now let's substitute in our highly suggestive notation and see what that actually gives us as our policy. So that's our policy. Now we'll substitute in the fact that V is log beta and Q is log beta STAT. And we get a policy that is the exponential of Q minus V. And we all know what Q minus V is. That is the advantage function. So now our policy is simply the exponentiated advantage function. And remember what I said before, that this particular model of optimality says that the optimal behavior is the most likely, and suboptimal behaviors become exponentially less likely. So it actually makes a lot of sense that we should have this as our policy, because the action with the highest advantage is the optimal one, and that's the one that gets the highest probability. And then as the actions get lower advantages, they become exponentially less likely. So we actually recover essentially the same intuition that we had before when we defined this model from this policy that takes actions with probability equal to their exponentiated advantage. Okay, so the summary of the policy computation is that our policy is the exponentiated advantage. You can express it also with a temperature if you want. So you can put a 1 over alpha in front of it. That can allow you to interpolate between fully deterministic policies, which you recover for alpha equals 0, and fully stochastic policies for alpha equals 1. It has kind of a natural interpretation. Better actions are more probable. You have random tie breaking. So if two actions are exactly equally good, you'll take them with exactly equal probability. And it's analogous to this thing called Boltzmann exploration that we saw very briefly when we talked about Q-learning. So it's kind of a nice exploration rule. You take actions with high probability if they're good, and if the action is known to be really, really bad, you never take that action. And of course, as you decrease your temperature, this gets closer and closer to a deterministic greedy policy. Okay, so at this point, we actually kind of have everything we need to create complete reinforcement learning algorithms out of this framework. We'll see how such algorithms actually behave after the break, but for now, does anyone have any questions about the policy computation, about question number 2? Okay, so let's go to the last question, the last inference question, number 3, which is the question of the forward messages. And this is going to seem a little bit arbitrary at first, but we'll get a little bit of intuition for what these messages do, and then next Monday we'll talk about how we can use them in an inverse reinforcement learning algorithm. So the forward message is the probability of a state given that you are optimal at all preceding time steps. So P of ST given O1 through T minus 1. And we're going to do the same kind of algebra stuff that we did for the backward messages. We'll just expand these out into integrals and integrate out the unobserved variables. And for the backward messages, we went from the back to the front. Now these are called forward messages, so of course we go from the front to the back. Which means that we're going to have to somehow put in ST minus 1 and AT minus 1. So we put in ST minus 1 and AT minus 1. We expand this out using the chain rule of probability, again into 3 terms. ST given ST minus 1, AT minus 1, and all our other stuff. AT minus 1 given ST minus 1, and all of our other stuff. And just ST minus 1 given the optimality variable. So 3 terms, just like before. For the transition, we know that it's, the next state is conditionally independent of the previous optimality given the previous state, so we can disregard that bit. And we're just left with these last 2 terms as the troublemakers. So we can collect all the terms. We know that AT minus 1 is conditionally independent of all the optimality variables before T minus 1. So we can just write it as AT minus 1 given ST minus 1 comma OT minus 1. And then the third term remains a little bit complicated. The ST minus 1 given O1 through T minus 1. So the first one, that's just the dynamics, that's all good. And it's just these second and third terms that we have to deal with. So what I'm going to do is I'm going to write out a really long equation. But what this really long equation is doing is it's just going to be applying, again, Bayes' rule to both the first term and the second term. So when I apply Bayes' rule to the second term and first term, let me just explain how I'm applying Bayes' rule. So for the first one, I'm applying Bayes' rule to flip the S and the A. For the second one, I'm applying Bayes' rule to flip the OT minus 1 only with the ST. And everything is still conditioned on O1 through T minus 2. So that's why for the second ratio, on the right side of the conditioning bar, I always have 1 through T minus 2. Why T minus 2? Well, because that's what's going to give me the forward message at the previous time step. So when I've applied Bayes' rule like this term and this term cancel. This term, the first term in the first ratio, is just the exponentiated reward. The second term in the numerator of the first ratio is the action prior, so that's a constant. And then in the second ratio, the denominator doesn't depend on S in any way, so up to a constant of proportionality, I can ignore that second denominator. And the remaining term in the numerator is just the forward message at the previous time step. So it's a little bit of an alphabet soup in terms of the equations, but everything has now been expressed in terms of the dynamics, the probability of optimality, and the forward message at the previous time step, which means that all these quantities are known. And of course, once I get back to time step 1, the forward message at time step 1 is just the probability of state 1, which is just the probability of starting in a particular state. Usually you assume that to be known. So we can calculate these forward messages. And now one interesting thing we can do is if we've calculated both the forward messages and the backward messages, we can actually calculate the probability of being in a particular state on an optimal trajectory. So P of ST given O1 through capital T. How do we do that? Well, we again use the definition of conditional probability. It's P of ST comma optimality divided by probability of optimality. We can break up the first term as probability of optimality given ST times probability of ST given all the past stuff. So we've basically broken this up into the future part and the past. So this is probability of future given ST, and then probability of ST comma past. So the probability of the future given ST, that's just the backward message. And then this bit becomes ST given past optimality times the probability of optimality at this time step. But this thing doesn't depend on ST. So that means that up to a constant of proportionality, we put in the forward message here, and we just end up with a probability of being in a state simply as the product of the backward messages and the forward messages. And those of you that are familiar with hidden Markov models, Kalman smoothing, and so on will recognize this as basically exactly the same derivation. So if you build forward messages, you build backward messages, you multiply them together, and you end up with a probability of being in a particular state along an optimal trajectory. This has kind of a neat graphical interpretation. So if you imagine that this is where you're going and that's where you're starting, your backward messages, you can think of them as kind of a cone radiating outward from the goal. And this cone represents all the states that have a high probability of reaching the goal. So if you start inside this cone, you'll be able to reach the goal. So this is the cone of large betas. And then there's a second cone radiating outward from the initial state, which is the cone of states that you can visit with high probability while getting high reward. So this is the blue thing is the cone of high alphas. And when you multiply them together, you essentially take their intersection. So your state marginals basically live inside the intersection of this yellow cone and this blue cone. And in particular, what this might lead you to expect is that if you actually have a kind of a geometric goal-reaching task like this, you would expect your state marginals to get wider and wider in the middle of the trajectory. That makes a lot of sense, right? Because if you reach the goal, of course, you have to have a pretty tight distribution at the very end. And if you start in a particular state, you have to have a tight distribution at the beginning. So you kind of radiate outward and then come back in. And that's basically the set of all trajectories less than a certain length that reach the goal. So that's kind of neat. In fact, if you actually do a little biomechanics study and you get a person to take a little pencil-type device and reach for different locations, you will exhibit a similar pattern of state distributions in those reaching motions. You'll actually see that people tend to have the widest range of states close to the midpoint of the trajectory that they execute. So this is from a paper by Lee and Todorov from 2006. that applies the principle of soft optimality to model reaching motions for humans. All right, so to summarize, I talked about a probabilistic graphical model for optimal control. That's this model. How you can frame control as inference, which looks a lot like hidden Markov models, extended Kalman filters, and so on. And you end up with a very similar backward recursion as dynamic programming of value iteration, but now with these softmaxes. So at this point, I'll take a little bit of a break. I'll be back when that clock hits 12:08, and then we'll discuss how we can create actual reinforcement learning algorithms out of this framework. So see you when that clock hits 12:08.
Regarding the notation, so the script O is not a variable, but an event that we are actually calling the optimal.
Right. So script O is a binary random variable, but we always set it to true.
Okay, so like in the expression, it's P of O equal to.
Yeah. So whenever I write P of OT given SDAT, I'm just being lazy. What I really mean is P of OT equals true given SDAT. Yeah.
When we're looking at P of AT given SD given optimality, that seems like it should be the optimal policy, but you keep calling it the near optimal policy.
Right. So this thing, P of AT given ST comma O 1 through T.
Yeah, exactly.
The reason I call it near optimal is because, of course, optimal in the traditional sense would be a deterministic policy that always gets the largest reward.
Okay.
So this policy does not get as large of a reward as the deterministic optimal policy. So I guess it's optimal for this model, but it's kind of approximately optimal in the sense that it's not actually it's not the one that gets the largest reward.
Sure.
Approximate, not in the sense that we're making any approximation, but approximate in the sense that the monkey is making an approximation, and we're trying to model the monkey.
Okay. I think that makes sense. All right, separate question. So we observe stochastic behavior in monkeys, and like we call it suboptimal, but is that just because like we're not evaluating the optimality?
Right. So yeah. So this is actually what we'll talk about after the break, is that everything is optimal for something.
Right. Exactly.
So it's optimal for a different objective, and we'll see what that objective is after the break.
Okay.
Did you have a question?
So it seems like the strict notion of optimality wouldn't scale well for high-dimensional action spaces.
Why not?
Your probability of optimality would just be so low at individual state and action pairs.
Oh, sure. So like these numbers numerically might be small.
Right. Does that have any practice? I mean, any?
Yeah, just take the log of everything.
I see. always.
The practical solution.
Oh yeah.
All right, let's resume. So one of the things I want to come back to is this optimism problem that I mentioned when I described the dynamic programming view of this backward message inference. So if you remember, the optimism problem was that under stochastic dynamics, our Q function here is given by the reward plus the log of the expectation of the exponential of the next value, which is not what we saw before, and it's actually kind of a problem. So why did this happen? Why did we end up with this weird thing here? Well, the reason this happened is because we kind of asked the wrong question. So our inference problem is to figure out the probability of a trajectory given optimality. And if you marginalize and condition this, you get the policy. You get P of AT given ST comma O 1 through T. And this query, intuitively, it's asking the question, given that you obtained high reward, what was the probability of your action? That seems like a very reasonable thing to ask. Like, I got $1 million. That means I obtained high reward. What was the probability of my action yesterday? But you can also marginalize and condition and get the dynamics. P of ST plus 1 given STAT comma O1 through capital T. And that is not equal to the real dynamics of the environment. Why? Well, because this is asking the question, given that you obtained high reward, what was your transition probability? So when I buy a lottery ticket, maybe I have like a 0.000000001% chance of winning the lottery. Everything else means I lose the lottery. But given that I got $1 million, given that you have that evidence, your posterior belief over how likely I am to have gotten lucky should be quite a bit higher, because you know that I actually got that $1 million. That's a reasonable thing to do. That's a correct thing to do from the standpoint of probabilistic inference. But it's a very peculiar thing to do from the standpoint of control, because of course you can't really plan to win the lottery. Yes?
But can't the O sequence be anything? Like, why are you assuming that they're all ones?
Right. So one possibility is, well, maybe the O sequence is not all ones. It turns out that this problem happens if there is any evidence in the future. So if your evidence is about the future, this optimism bias will take place. The intuition behind it is that there's nothing that sort of privileges the policy over the dynamics. They're both just two CPDs in a big graphical model, and they'll both change in the posterior given your evidence. So if you want to address the optimism problem, what you really need to do is you need to ask a slightly different question. So what you want is this thing, the top thing, given that you obtain high reward, what was your action probability? And you don't want that second thing. Because that second thing basically amounts to assuming that you got luckier simply because you believe that you were being optimal. Some people do think this way. They think, well, because I'm so smart, I'll be getting luckier. But that's not really how the universe typically works for most of us. So what you really want to ask is something more like this. Given that you obtained high reward, what was your action probability? Given that your transition probability did not change. So given that you were no luckier than you usually are, but you got high reward, what was your action probability? That turns out to be a pretty difficult question to ask in a classic probabilistic inference framework, but with a little bit of a trick, we can make this work. So what you need to do is you need to find another distribution that we're going to call Q that is close to P. So a distribution Q over states and actions that is close to the posterior over states and actions given O, but has the same dynamics as P. So where have we seen that before? Where have we seen this problem of finding one distribution Q that is close to another distribution P in order to solve inference problems? Well, if you guys watched the lecture that I asked you to watch on Monday on variational inference, you will have hopefully seen it there. For those of you that didn't watch that lecture, you'll probably find the next 5 minutes to be very, very confusing. But hopefully you've seen variational inference material before, or you watched that lecture. All right. So in variational inference, we're concerned with latent variable models, as you learned about in that lecture. And in our control formulation, the latent variables are basically the trajectory. So that's the bit that we don't observe. What we observe is the fact that we're optimal. So our evidence, our x, is the optimality variables. Our latents, z, are our states and actions. That might seem a little bit peculiar from an RL standpoint, because in RL we saw that, well, you observe states and then you take actions. But here we're talking about the inference process. So the s's and a's are actually our latent variables. And in variational inference, we find a q of z to approximate a posterior p of z given x. And that's what we're going to do here. So let's try variational inference. So let's write down a variational lower bound that expresses this likelihood, which is what we want, in terms of our approximate variational distribution q. And then we'll choose a particular form for q that eliminates the optimism problem. So let's do control via variational inference. We'll choose the following form for q. And this form is, from a variational inference standpoint, this form is weird, but it'll really work well for us. So we'll choose q to be factorized much like the MDP, except that it will not have those optimality variables, because that's our evidence. The evidence doesn't belong in the q. But it will have this additional edge, q of a given s. The initial state and the transition probabilities will be chosen to be exactly the same as they are in P. So that's basically encoding our assumption that the transition probability did not change. So the transition probability did not change means use the same transition probabilities that were in the original MDP and the same initial state distributions. So the only new thing in the Q is the action distribution, A given S. And that's going to become our policy. So our original graphical model has states, actions, and optimality variables, and these are the CPDs in that model. Our variational distribution looks like this. It has a new edge from S to A, which is going to represent our policy, and it has the same transition dynamics and initial state distribution. So remember that our observations, our x's are O, and our latent variables z, those are the s's and the a's. So this is our actual posterior z given x, and this is our variational distribution q of z. So now if we write out the variational lower bound, this is just the equation from the video lecture that you watched expressed in terms of x's and z's. So the variational bound is the expectation with respect to q of z of the likelihood log p of x comma z minus log q of z. And in that variational inference lecture, you saw that this, the right-hand side, was in fact a bound on the likelihood, which means that if we optimize the right-hand side, we will in fact optimize the likelihood. And the bound is tighter and tighter as q gets closer to the posterior pz given x. So that second term is basically the entropy of q. So now what we're going to do is we're going to substitute into this equation the p and the q that we chose for our control problem. So this is our q, just like the same as on the previous slide. And we'll substitute that in, and now I'll write out the variational lower bound one term at a time so that you see how it comes together. So first, well, everything is an expectation under q, good. Then we'll walk through the terms in the log p in the likelihood. So that has the log p of S1, the sum over all the time steps of the log probabilities of the transitions, and the sum over all the time steps of the log probabilities of the optimality variables. Right? So these are just all the CPDs in the p. Now let's go through the q. So we have a minus log q. So that means, so we'll just substitute the terms directly from this equation for q. We have a minus log p of S1, that's this first one. Then you have a minus sum over all the time steps of the log probability of the transitions. And then you have the only new thing, which is the log q of A given S. So now it's probably immediately obvious that a lot of stuff here cancels out. So we have a plus log p and a minus log p of S1. We have a plus and a minus for the dynamics, so those cancel. And if we collect the only remaining terms, we get an expectation under q of the sum of the rewards minus the log q's of A given S. And this is starting to look an awful lot like the reinforcement learning objective. Where did the r's come from? Well, that's just the log p of O. So if I take the sum outside of the expectation, I can also write it as a sum over time steps of the expectation under the state action marginal of q of the reward at that time step plus the entropy of my policy. And this is very similar to the reinforcement learning objective, with the only difference being the entropy term. Well, that's kind of cool. So that means that I can bound my likelihood with the expected reward plus the entropy. So that means you maximize your rewards and you maximize the action entropy. Now, this bit I'll probably not actually go through in detail in today's lecture, but I'll just give you the punchline here. You can walk through a dynamic programming formulation for optimizing this bound. And if you walk through the dynamic programming formulation, all the equations will be in the slides, you'll actually end up with an equation. I'll just go here. You'll actually end up with an equation for the Bellman backup where the q is now expressed as an expectation of v just like before, but the v is still a softmax. So if you want to go through the full derivation for this, check out the slides, which will be on the website. It's a little tedious, but it's reasonably straightforward. And the punchline is that once you have that particular variational distribution, then the q equation, which before was log of the expectation of the exponential of v, now becomes just the familiar expectation of v because of how we chose q, little q. All right. So just the summary of the variational version of the backward pass, it looks very much like it did before, with the v still given by the softmax, but the q function now just has the expectation of the next value function instead of the log of the expectation of exponentials. So now we're even closer to the classic value iteration algorithm. The classic value iteration algorithm computes the q using the expected value at the next step and the v as the max. This soft value iteration algorithm computes the q in the same exact way, but the v as a softmax. So softmax here refers to the log of the sum of exponentials. Okay, so to summarize this variational stuff, our original graphical model looked like this. We introduced a variational distribution, which eliminates the O edges and introduces an additional edge from S to A. That results in a dynamic programming algorithm where the value function is still a softmax, but the Q function has a regular expectation. You can find a bit more details about this in this review, and you can also look through the slides to see the summary of the dynamic programming procedure. There are a few variants on this process that are worth knowing about. So you can introduce a discount into this to get discounted stochastic optimal control. Works exactly the same way, you just put a discount in there. The way that you typically justify this is by saying that you're modifying the transition dynamics. You can also have an explicit temperature. So when you take these exponentials, you can put a 1 over alpha in front of the Q and an alpha out front, which will result in a situation where as alpha goes down, the softmax approaches a hard max. So you can use this to actually interpolate between a classic RL formulation, which you recover when alpha equals 0, and the stochastic one, which you recover when alpha equals 1. And that can be convenient in practice if you want to actually control the degree of stochasticity that you get. Okay. Does anybody have any questions about this derivation before I present some actual practical algorithms based on this idea? All right. So one of the things you could do is you could modify standard Q-learning to introduce this notion of soft optimality. So in regular Q-learning, this is exactly what we saw before. You update your Q function parameters by using the gradient of Q times the Bellman error, times R plus next value minus the current Q value. So this is exactly what we saw in the Q-learning lecture. And your target value, V of S prime, is typically calculated by taking a max. If you turn that max into a softmax, that's the only change you make, then you get a soft Q-learning algorithm, which calculates these backward messages. So with that very, very simple change, you're actually calculating backward messages in Q for the variational version of this algorithm. The one detail is that after you've done this, when you actually choose your policy, instead of being greedy and taking an action with probability 1 if it has the largest Q value, in principle what you should do is you should use the exponentiated advantage. So you should do the Boltzmann exploration as your final policy. So the resulting procedure, it's still an off-policy learning algorithm, so when you explore, you can actually take your actions however you want, get your mini batch, compute your target value, but use a softmax, take a gradient step, update your target parameters, etc. Everything's exactly the same as the Q-learning we saw before, with the one and only difference being the word soft right there. But there's, of course, another difference, which is once you're done learning, in principle, you should use the exponentiated advantage as your policy. Of course, no one's going to stop you if you want to use the most likely action as well. In fact, that might likely be better in terms of getting you better reward. You can do policy grading with soft optimality as well. So if you don't bother with all this dynamic programming stuff, and you just stop right at the point where you derive the objective being expected reward plus entropy, so you could stop right there, not worry about dynamic programming, and just directly use policy gradient to calculate the derivative of this quantity. So the only difference at that point is the entropy term. And the entropy term is actually not too hard to deal with. So the policy gradient has kind of a nice intuition. The intuition is that you're taking your policy to be proportional to the exponential of the Q value, which is minimizing the KL divergence between your policy and exponentiated Q. So that's kind of neat. You turn RL into KL divergence minimization. So people sometimes refer to it as entropy regularized policy gradient. Why entropy regularized? Well, because you have expected reward, and then you're adding this entropy, which regularizes your policy, keeping it from becoming too deterministic. So in practice, this can actually really help with policy gradient, because if you remember the discussion of natural gradient from before, if you have a variance term, like let's say you have a Gaussian policy and you have a variance and a mean, the variance always wants to go down, because reducing variance will usually make your policy better. And that in practice tends to result, especially if you don't use natural gradient, in the policy gradient prematurely collapsing the variance, reducing your exploration, before it actually finds a good mean, before it actually finds a good behavior. So in practice, adding this little entropy term to policy gradient can get it to optimize a lot better. In fact, people have been using this term long before they actually realized the mathematical framework that it corresponds to. So the entropy regularizer was used as a heuristic modification to policy gradient long before it was actually determined what notion of optimality it actually corresponds to. It actually also turns out, as a funny observation, that when you include the entropy term in policy gradient, the resulting gradient that you get looks eerily similar to Q-learning. This connection is, can be made more precise, although it's still a little bit imperfect in many cases. The reason it's imperfect is because Q-learning is not exactly policy gradient is not exactly Q-learning, but they are very closely related. I think I can go through that connection briefly. So to go through that connection, we first derive the policy gradient for the entropy regularized case. So the only difference here from regular expected reward is that now you have this expectation of negative log pi. That's what the entropy is. So you can write it like this, r minus log pi. And then you take the gradient. Now when you take the gradient of this, you basically just apply the policy gradient with this thing as the reward. But there's one little detail, which is that the log pi also depends on the parameters theta. So you have to also take the gradient of that. But the gradient of negative log pi is just grad log pi. So since our policy gradient already has a grad log pi in there, all we do is we modify the reward with the negative log pi, and then we subtract 1 at the end to account for that extra grad log pi term that comes from this. And of course, subtracting 1 makes no difference, because we saw before that we can baseline the policy gradient with any constant, and it will be equal in expectation. So that means that we can just disregard this thing and simply modify our reward to have a negative log pi in it, and we actually get the right policy gradient. And then choose whatever baseline you want. So that gives you a policy gradient with entropy regularization. You can ignore this. It goes into the baseline. And now, if I want to connect this up to Q-learning, what I'm going to do is I'm going to say that this bit, this is just my Q function at the next time step. So the sum of rewards in the future, Q of st plus 1, at plus 1. I'll keep the r here. The r I want to keep, but this I'm going to make the next Q. And then I'm going to substitute it in my equation for pi, because I know that pi is exponential of q minus v, so log pi is qst minus vst, so I'll take these things and I'll put them in there for my log pi term. And then I can rewrite this gradient as the gradient of q minus the gradient of v, so that's just my grad log pi. So my grad log pi turned into this thing. And then inside the parentheses I have my r, the next q value, minus the current q value, plus the value function. So these last two terms came from the log pi. This qst plus 1, at plus 1 came from these collected terms. And this is just the current r. I'm going somewhere with this. So the v I don't care about, because the v is the baseline, right? Because any state-dependent function can be added in there and it'll be unbiased in expectation. So once I cross out the v, now I've got something in here inside the parentheses that looks like Bellman error. I have r plus next q value minus current q value. So if I were to write it side by side with the Q-learning gradient, and remember the Q-learning gradient is gradient descent, the policy gradient is a gradient ascent, so there's a negative sign in front. If I write my Q-learning gradient, I also have a minus q, just like here. In off-policy Q-learning, I take a max over the next q, whereas here I just add it. So this is an on-policy method. Since it's an on-policy method, I don't need to do the soft max. This is off-policy. And then the only other difference is that in Q-learning I have a grad q. In policy gradient I have a grad q minus grad v. So the gradients actually end up looking pretty similar. This is the high-level kind of hand-wavy version of this. If you want a more precise version, what I recommend is checking out these two papers, which I'll have complete citations for at the end of the slides. But that's kind of the high-level intuition, that you get gradients for soft Q-learning that look an awful lot like gradients for entropy regularized policy gradient, which maybe suggests a connection between the two. OK. Now, why might we want to actually build complete reinforcement learning algorithms out of these components. So for policy gradient, as we discussed, the benefit is that your entropy doesn't collapse, so you actually tend to explore a little bit more, and adding that entropy term to the policy gradient is very easy, so that tends to be quite desirable. It turns out to be especially easy to specialize or fine-tune policies trained with soft optimality for downstream tasks. Because if your policy doesn't collapse to a very deterministic behavior, it might be then easier to specialize it to new behaviors later on. We'll see some examples of this in a second. It provides a principled approach to break ties. And you turn out to get better robustness, because when you maximize the entropy of your policy, what you're doing is you're basically asking it to solve the task in many different ways. If downstream some of those ways of solving the task become invalid, because maybe something about the environment changes, the other ways of solving the task might still be applicable. And of course, you can reduce this to regular conventional hard optimality as your reward magnitude increases, or if you put a temperature on it, if you drive that temperature to 0. And of course, as we'll learn next week, it's also a good way of modeling human or animal behavior for inverse RL. OK, so in the last couple of minutes, I'll skip the review bit. What I want to show is a few examples of soft optimality in action for an actual RL algorithm. So one of the things we can imagine doing, I'll just skip this intuition. So this is basically soft Q-learning, just like I described it in the slides. One of the things you can imagine doing is running soft Q-learning with an underspecified reward function. So in this video that you're about to see, on the left side, this is showing a deterministic method. This is actually DDPG, but most deterministic methods will produce similar behavior. On the right-hand side is soft Q-learning, which tries to maximize the entropy of the behavior. And here the reward function is to get this little ant robot, which some of you might have tried for homework 1, to run as fast as possible in any direction. So the reward is just magnitude of speed, regardless of where it's going. Now you might think this is kind of a useless thing to do, but we can do it anyway and see what happens. And what you can see is that the soft Q-learning policy looks terrifying. It looks like kind of a Halloween appropriate sort of animation. But more importantly, it runs in all directions. So it's like this explosion of these little spider-like things running in all directions. Now, why might this be desirable? Well, this might be desirable because the underlying Q function for this just learned how to run in all possible directions, which means that if we want to then specialize it to do some navigation task, we might think that that might be a good starting point. It already knows how to run in all possible directions, so all it has to do is remove those directions that are not appropriate for the downstream task. So let's give it a downstream task. Let's ask it to run as far as possible down this hallway, and we'll compare an agent initialized from scratch, initialized from the deterministic Q function on the left, and initialized from the soft Q function on the right. Of course, initially the soft Q function runs in random directions, so it's not actually making progress down the hallway. But then as it trains, you'll see that the soft Q function specializes a lot faster because it essentially already knows how to walk in all directions, so it just has to discard all the directions that are not useful. Whereas the other initializations, the random one and the deterministic one, need to essentially unlearn whatever they have and then relearn running in the right direction. So you can do a substantially better job of pre-training. And you can look at the quantitative plots. The blue line is the max-length initialization, and it tends to fine-tune quite a bit faster on a range of tasks. OK, so that's sort of one of the benefits. The main reason I want to introduce this mathematical formula is because it's very useful for inverse reinforcement learning, but it can also be a really useful component in lots of robust and fine-tunable RL methods. OK, so see you all next week for a discussion of inverse RL, and I'll be around in office hours after class to answer more questions.